Okay, in the last section of part of section 2, we're going to look at how we do a test on the difference of two means. Very similar to how we did the difference for two proportions, we're going to find a test statistic, in our case t, which is found by just the difference of the two sample means minus the difference of the two hypothesized means. This is always 0. So really this t value is really x1 minus x2 bar. And then all over this standard error, square root s1 squared over n1 plus s2 squared over n2. So this is how you'll find your t, and then we can use our chart to approximate the p-value. Or we'll also have a technology, the two-sample t-test, that will be able to find both the t-value and the p-value. So the only thing we really have to remember is our degrees of freedom. I mentioned in the last section there's a really hard formula for degree of freedom, and here it is. So this is the way we typically find degrees of freedom, which is kind of a pain. So instead we just use the approximate, whatever is smaller between n1 minus 1 and n2 minus 1, just like we did with the intervals. So we're really just doing the same thing. We'll find the standard error, find the t-value. We're using the chart. If the p-value is smaller than alpha, we'll reject. If it's not, we will fail to reject. So here is a big list of data. So we have the mean number of pearls harvested from two different estuaries. And we want to test if there is a difference between these two at alpha equals 0.10. So the first thing I'd do is I would define these both as means. So maybe I'd call mu1 the average number from estuary A, and mu2 is the average number from estuary B. That way when we write our hypotheses, we'll kind of know what we're talking about. So the null would say they are just equal, which means their difference is 0. In our alternative, we're trying to see if there is a difference. We're trying to see if they are different. We don't really care which one is bigger than which, but we want to just know if there is a difference. So before I go any further, the first thing I'll have to do is find what is the average and the standard deviation of this big list of numbers. So I went ahead and I found the average, the sample mean for estuary A, so we'll call it x bar 1. So that was 407.15 with a standard deviation of 59.53. And of course I sampled, there were 20 in this data set. So those are all the sample data just for estuary A. Put them all in your calculator, run your one variable stats, do them by hand. Those are your values. And then we do the same thing for estuary B, which we'll call 2. We'll find x bar 2, S2, N2. So estuary B, the mean I found was 327.05. Sample standard deviation was 54.07. And this one also had 20 in our value. So what we'll do is to find our t-value, remember our t-value, we're going to take the difference between the two sample means. So I'll do 407.15 minus 327.05 minus 0 because the difference is 0, divided by the standard error, which is the big square root, 59.53 squared over 20 plus 54.07 squared over 20. Just using that chart, that formula, and then we can use our chart. So this becomes a positive 4.45. So now to get my p-value, I have to know my degree of freedom. Now my degree of freedom is the minimum of one less than the two sample sizes, so my degree of freedom is 19. So I'm going to go to my chart. I'm going to go to my t-chart, and I'm going to look for what is the value where 4.45 is between, and actually the very last number on my row of 19 is 3.883, and 4.45 is bigger than that. So I'm just going to use that value at the top of that column. So I know the p-value is going to be less than 0.0005. Now, of course, we can use our technology, and we'll make another video to show you how to use the technology, and it will give you the actual p-value. The p-value from the technology will turn out to be 0.0001, so definitely smaller than what we have. So when we do that, you'll see how that works out. But irregardless, since the p-value is less than 0.10, which was our alpha, we'll reject the null. And in rejecting the null, we're saying there is evidence to show a significant difference in the mean number of pearls produced. So there you go. There's a complete problem from start to finish by hand. Really didn't use much technology, well, except for to find the means. But with the technology, it obviously makes it much, much simpler. Let's look at another one. This one says a researcher is trying to see if adding chocolate to the stingray diet will increase the stingray activity. To do this, the researcher collected the following data. So we have some data on the regular diet and the diet with chocolate. And it's saying, is there evidence to show adding chocolate increases the daily activity? So we're trying to see is the diet with chocolate greater than the diet with regular? So you can actually call these anything. If I call mu1, I'll call it the average diet, average activity, sorry. Average activity on the regular diet. And we'll call mu2 the average activity on the chocolate diet. So our hypotheses, the first one's always going to be real simple. It's going to be that they're equal, that there is no difference. But now we're saying, is the chocolate greater than the regular? Is the activity more on the chocolate than the regular? So a couple ways you can write that. Since I have mu1 is this one, and mu2 is this one, if I want to put it in the same order, it would be mu1 less than mu2. I could obviously switch these both and make it mu2 equal mu1 and mu2 greater than mu1. That works too. Really up to you. I'll just stick with the first ones. Since it's less than, because saying the regular is less than the chocolate, I should get a negative t value, hopefully, but everything else will work very similar. So I already kind of have my value, so I'll go ahead and do my t, which remember, let's just go ahead and write it down again, because that'll be helpful. So I'm just going to plug this stuff without using technology into this formula. So I'm going to get 23.2 minus 27.8, all divided by the square root 3.4 squared over 32 plus 2.8 squared over 45. If I've done this correctly, it should give me a negative value. So I get negative 6.28, which is just really a ginormous t-value. Now our degree of freedom is going to be the minimum of those two, so the degree of freedom is going to be 31. So when I go to my chart, there is no 31, so I'll just go up to 30. And 6.28 is way past it, so similar to the last problem, the p-value is going to be less than 0.0005. Now again, when I'm doing my technology basically says it's 0, because it's so small. So it's definitely going to reject. So since the p is smaller than alpha, which we just assume is 0.05 because it's not given, we say there is evidence that the stingray is significantly more active on the regular diet. Or no, pardon me, not on the regular diet. It's exactly the opposite of what we concluded. It's on the chocolate diet. Obviously a fictitious example because I'm pretty sure that's not good for a stingray. So nothing too crazy. You set up your hypotheses. You find your test statistic. You find your p-value from the chart or with technology. If it's smaller, you reject. If it's bigger, you fail to reject. And then you make your conclusion.